Today we're going to discuss how to use the finite difference method to solve a partial differential equation using the Poisson equation to demonstrate. We'll begin by reviewing the Poisson equation, and then we'll discuss the finite difference method for rectangular domains, trapezoidal domains, and annular domains. To begin, recall that the Poisson equation is a partial differential equation of the following form. The sum of the second derivatives with respect to each independent variable is set equal to some known function f of our independent variables. In 2 dimensions, that is, where the unknown function takes 2 inputs, an example would be the following, where e to the x plus y is our known function f. We can write this as delta u equals f, where delta u here means the Laplace operator, which means to take the second derivatives of the function and sum them. In higher dimensions, we continue to use the Laplacian notation to save space, but we always refer to the equation Laplacian of unknown function u equals known function f as the Poisson equation. The Poisson equation does not have unique solutions unless you specify some additional conditions, known as boundary conditions. Boundary conditions specify something about our unknown function u along the boundary of the domain. So the Poisson equation really looks like this, where we specify that we're solving it on a rectangle. That is, the unknown function u is to be defined only on that rectangle. Moving on, there are 3 common types of boundary conditions. The first is called Dirichlet boundary conditions, where we specify the value of the function u along the boundary of the domain. Note that we don't have to specify the value to be constant. It can vary. For example, on the top side, we have it increasing as we increase the x value. But it is specified and known. The second type of boundary condition you commonly see is called Neumann conditions, where we specify the normal derivative of u along the boundary of the domain. Note that if our domain is a rectangle, this is the same as specifying either du dx, du dy, or their negatives. Finally, there are Robin conditions, where we specify the value of a linear combination of the normal derivative of u and the value of u, with the weights in the linear combination allowed to vary spatially. Here, we're using a to denote the weight on u, the unknown function itself, and b to denote the weight on du dn, the normal derivative of the unknown function, and c to denote the right-hand side of this equation. The subscript t denotes that they are weights in a Robin condition that applies to the top side of the rectangle. If it were the right side of the rectangle with a Robin condition, we'd be using the subscript r. You'll see this being used later in the video. If you're curious, Robin conditions come up in Newton's law of cooling, where the heat flux through some side is related to the temperature there. Finally, note that we don't have to specify the same type of boundary condition on all parts of the domain. Altogether, the Poisson equation with some boundary conditions is known as a boundary value problem. This is one of the most common types of problems seen in physical applications. Moving on, let's discuss how to solve this boundary value problem using the finite difference method. The finite difference method is made up of 3 steps. The first step is to discretize your domain. The second step is to discretize your problem, which converts the PDE into a system of linear equations, 1 equation per grid point of your discretized domain. The final step is to solve the discretized problem, that is, to solve the linear system. The result will be a function defined only on the discrete domain, not defined on the original continuous domain, and whose values will have some error from the values of the true solution at the same points. That is, the result is both an approximation and is defined only on a finite number of points in our domain. This is very abstract, so let's study these steps in detail. what do we mean by discretizing our domain? For a rectangular domain, this is typically done by subdividing the rectangle into squares, forming a grid where we create n+1 discrete horizontal positions in the grid and m+1 discrete vertical positions in the grid. That is, our x values go from x0 to xn, and y values go from y0 to ym, with the separation between consecutive horizontal or vertical positions being some constant h. For an annular domain, this is typically done by subdividing the annulus in angle and in radius, where our radius values go from r0 to rn, and our angle values go from θ0 to θm. For a domain that's not an annulus or rectangle, which we'll typically call an irregular domain, using the finite difference method gets more complicated. If we have a piecewise linear boundary, then the discretization process is still very doable. However, it'll be more complicated to code and solve the resulting problem. For an irregular domain that has curved boundaries, it's best to use a different method, like the finite element method. Moving on to step 2 of the finite difference method, we have to discretize the problem. Recall that our problem is saying that at all points x, y in the continuous rectangular domain, we want this statement to hold. The discrete version of this problem would be, at all points xi, yj in our discrete rectangular domain, we want some discrete version of this statement to hold. What is the discrete version of this statement? As you might suspect from the name finite difference method, it's the statement we get by replacing every derivative seen in the PDE with a finite difference approximation, which is an approximation of a derivative of a function using the value of that function at finitely many points. Basically, it's estimating the derivative of a function at one grid point by using the values of the function at neighboring grid points. We won't discuss the derivation of this approximation in the video, so let's just take it for granted that this is a good approximation of the derivatives in our problem. Note that we use the value at, above, and below the grid point to estimate the y second derivative, and we use the value at to the right and to the left of the grid point to estimate the x second derivative. Note that this result is only approximately true. The function that satisfies the exact version of the statement is not the same function as the one that solves the PDE, so let's refer to it by w. Here I've also rearranged the expression so that like terms have been grouped. Note that w has some error from approximating derivatives as finite differences, and also the function u that solves the PDE is defined in a domain with infinitely many points, whereas the mathematical object w that we're constructing by solving this discrete problem is a function of finitely many points only, the grid points ij. Because we have a finite number of points at which we need the discrete version of our statement to be true, we end up producing a finite number of linear equations that we then solve as we would solve any linear system of equations. The variables here being w sub ij, which are the values of our approximation w at each grid point ij. In the figure shown on the screen, we're excluding grid points on the boundary, that is, grid points with index 0, n, or m, because we're assuming that those values are known and are not variables we need to solve for. In other words, that we have Dirichlet boundary conditions. We'll cover the case where we have non-Dirichlet boundary conditions later in this video. The color coding shows where each term in each equation comes from spatially, as the y derivative at the central blue node is approximated using the green nodes above and below it, and the x derivative at the central blue node is approximated using the purple nodes to the right and left of it. As with any system of linear equations, we can assemble our equations into a single matrix equation, where we've assigned some ordering to our grid point. The order in this case is such that we go from the left to the right and from the bottom spatial row to the top spatial row. Note that for some of the equations, there are actually less than 4 variables, because in this example we have Dirichlet boundary conditions, meaning any values that occur on the boundary are actually knowns and not variables. In those cases, they need to be moved to the right-hand side vector. This occurs at the first and last node of each row, as well as every node of the first and last rows of our grid. The right-hand side vector also has one term from the known function f at each grid point. The color coding in the matrix once again tells you where that matrix element comes from spatially. Note that the matrix has a nice structure to it. In particular, it's a block tridiagonal structure, so we can rewrite it as follows for clarity. The tridiagonal blocks d sub k come from the x derivative estimation. The identity blocks I come from the y derivative estimation. Each block row in the matrix corresponds to one spatial row in our domain. And once again, the matrix rows that correspond to grid points that are at the ends of a spatial row have a different expression in the right-hand side vector, as do all of the block rows that correspond to the first and last spatial rows of our domain. If we solve this system using MATLAB, we get a vector whose entries are the value of our approximate solution W at each node of the grid. If we make the grid size smaller, there will be less error in our approximation. However, for problems involving more complicated boundary conditions or non-rectangular domains, it'll be more complicated to set up this matrix, and iterative methods for solving the system could also be faster due to the sparse nature of this matrix. In this video, we'll look at the simplest iterative method to solve linear systems, Jacobi iteration. To review, Jacobi iteration means we rewrite the kth equation in our system by solving for the kth variable in terms of the others. Or in this case, where our equations are spatially indexed by I and j, we solve for wij in terms of the other variables to get the following. And then the iterative part is that we start with some initial guess, maybe that all variables which don't have specified values from the boundary conditions are 0, and plug these into the variables on the right-hand side to get a new value for the variable on the left-hand side. Once we've done this for all the equations corresponding to non-boundary grid points, we'll have a new set of values that are assigned to each variable. This is known as completing the first iteration. Using the updated values from our first iteration, we go back to the first equation and repeat this process until we have another updated set of values. Then we would have completed our second iteration. Continuing this way, our values stored in the updated guess vector should approach the solution to the linear system with arbitrary accuracy. As you might expect, on a computer this process is accomplished using a loop. Note that if we have Dirichlet boundary conditions, we don't have to be careful around which w's are variables and which are knowns in the formula. Instead, we just need to be careful that our computer program only applies this formula to points that are not boundary points. That is, we just need to be careful with the range of indices that we loop over. Before we cover what to do with non-Dirichlet boundary conditions, let's go over an easy example. We have here a rectangular domain with x values from 0 to 1 and y values from 0 to 1/2. The boundary conditions are Dirichlet, and we've specified a value of 0 along the blue sides and a value of x times 1 minus x along the green side. From this function, we can already say that wi0 should be xi times 1 minus xi. The only nodes we need to determine the value of are the red nodes in the middle of the rectangle. Now, our iteration formula is on the screen. During each iteration, we'll be evaluating this formula at 1, 1, 2, 1, and 3, 1. If we plug in the values of our boundary for the green and blue variables, we get the following, which is what our computer will actually be using to update the values of W11, W21, and W31. After the first iteration, since the red variables are all initially 0, we get the following vector of new values. Using these new values, and continuing in that way, we approach the following. Now, there could be a lot of error between this and the solution to the PDE because our grid spacing is really large relative to the size of the domain. But there will be very little error between this and the actual solution to the linear system for our approximate solution W. Let's move on to the non-Dirichlet boundary conditions on rectangular domains. In this case, the boundary points are actually variables, not knowns. So for one thing, we'll have more variables in our linear system. But more importantly, how in the world do we apply the iteration formula to a boundary point when there might not be a left grid point value at all? Well, we can't use this exact formula, and as you'd expect, the same goes for boundary points on the top, bottom, or right sides of the rectangle. So in our computer program, we'll use this formula only when we have an interior point. The real trouble comes in figuring out what to do with the boundary points. The way to handle this is with what are known as fictitious nodes. Essentially, we're going to imagine that there is a node outside the domain, or in this case, to the left of the boundary node. It has an x-index of -1. Now, since Robin boundary conditions are the most general boundary conditions commonly seen, let's suppose that we have some Robin boundary conditions specified on the left boundary and Dirichlet conditions everywhere else, with the Dirichlet parts of the boundary in green. Our iteration formula does not work at the left boundary nodes because of the red term that does not exist. But if we pretend it does exist, what value should that node have? There's a natural way to determine the value this fake node should have because we do know something about the boundary. Specifically, we know our boundary condition. The text in blue needs to hold at the boundary nodes. The discrete version of this boundary condition can be found by substituting a centered finite difference approximation of the normal derivative of u in terms of the values at the left and right grid points, and then replacing the symbol u by w and changing the statement from approximate to exactly equals. We then rearrange to solve for non-existent node w sub -1j in terms of nodes that do exist. Finally, we substitute our value into the iteration formula to get the boundary point iteration formula. Notice what really happened here. The real node in blue that's opposite the fake node gets its coefficient doubled from 1 to 2. The other nodes keep the same coefficient. The denominator out front goes from 4 to 4 plus some a over b term, while the parentheses get an additional c over b term. Take a moment to appreciate this clever method of handling non-Dirichlet boundary conditions. We have some knowledge about the boundary and some knowledge about interior nodes near the boundary, and we combine them to obtain knowledge beyond the boundary, which we then use in our updating formula on the boundary. Now you can imagine that if we have a non-Dirichlet boundary condition only on the right, or only on the top, or only on the bottom of the rectangle, then the process is very similar and we get the formula for the boundary points by making the same modification. We add some a over b term to the denominator, and add some c over b term to the stuff inside the parentheses, and double the coefficient of the node opposite the fake node. It gets more complicated if we have a non-Dirichlet boundary condition such that we have a non-Dirichlet corner boundary point, because in that case we have two fictitious nodes. But the calculation of the value of one of them is not connected to that of the other, So it turns out that we make the same symbolic changes to the formula. Moving on, it's easy to apply the finite difference method to solve three-dimensional Poisson equation problems as well. Instead of discretizing the domain into squares, we discretize it into cubes, and we use the same fictitious node approach if we have non-Dirichlet boundary conditions. We use the same finite difference approximations for the second derivatives in each direction as well, and we get a pretty similar formula. It's harder, but still doable, to apply the finite difference method to trapezoidal domains. By trapezoidal domains, we mean domains that have one slant side and three sides parallel to the x or y axes, or domains that have two slant sides that have the same or opposite slopes and the other sides parallel to the x or y axes. Basically, we're excluding scalene trapezoids and also ensuring that two sides of the trapezoid are aligned with the x and y axes, because this makes it simpler for now. Let's use the case of a trapezoid with a single slant side as an example. If we choose the x difference to equal the y difference in our grid, then we end up with nodes that are missing neighbors. What we have to do is pick the ratio delta y to delta x to equal the magnitude of the slope of the slant side. Note that you'll have to pick delta x to be the least common multiple of the side lengths of the straight sides so that we aren't missing any nodes on the other parts of the boundary. If we do this and we have Dirichlet boundary conditions, the formula we use is not quite the same as for the rectangular case, but it's pretty similar. The problem is that the x difference is not the same as the y difference, so the factor lambda, which relates delta x to delta y as seen here, comes into the formula. We use this formula exactly how we did the other formula, looping over the interior nodes and updating their values when doing Jacobi iteration. However, there is again a problem if we have non-Dirichlet boundary conditions. In that case, if the non-Dirichlet boundary condition is on a non-slant side, then we can use the same approach from earlier in the video, where we have a single fictitious node and substitute the centered finite difference approximation for the normal derivative into the Robin condition. As an exercise, try to derive the boundary point formula for this case. Moving on, the real difficulty comes when we have a non-Dirichlet boundary condition on the slant side. In that case, we'll have two fictitious nodes, and not only that, but the normal derivative is not as simple as the x derivative or the y derivative. In this case, the normal derivative requires that we combine the x and y derivatives in some way. Thankfully, we have everything we need to figure out what combination this is. We know the slope of the slant side in terms of delta x and delta y. For the example shown on the screen, the slant side has a negative slope with magnitude delta y over delta x, because that's how we chose them. So the outward normal vector will point in the direction delta y, delta x. If we then normalize this vector to have magnitude 1, we get the unit normal vector, which if we take the dot product with our estimate of the gradient using center differences, we get our discretized approximation to the normal derivative on the slanted boundary. We can then substitute this into a Robin condition. Let's also save space by calling the square root value delta r. Now here's the tricky part. We can't solve for only one of the values of the fictitious nodes in terms of non-fictitious node values, because now we have both of them appearing in the Robin condition at the same time. What we can do is solve for the value of the linear combination of both fictitious node values entirely in terms of non-fictitious node values, so that we can substitute it for the combination in the formula. At that point, we're done. Working with this Robin condition, we get the combination we want to solve for in terms of non-fictitious values has the following representation in terms of non-fictitious values. Substitute this into the formula and simplify to get our result. Let's move on to our last type of domain, annular domains. By an annular domain, we mean a physical ring shape where there's some inner radius and some outer radius, and the shape covers some range of angle values. As you can imagine, polar coordinates express this domain better than Cartesian coordinates. What we have to do is once again discretize the domain with maybe n intervals of radius and m intervals of angle. Now, notice that this discretization makes it really hard to use our nodes which are neighbors with respect to radius or angle to estimate derivatives in the x and y directions. The solution to this issue is to convert the Poisson equation into polar coordinates, which I'll leave as an exercise for you. But here's the result of that conversion. Recall that by changing coordinates, we mean that the solution to this new equation with boundary conditions will be spatially the same function as the solution to the original problem. But mathematically, the function object will be different because its inputs are interpreted as referring to the domain in polar coordinates and not in Cartesian coordinates, which are what the original problem and its solution function are using. As before, we have to discretize the problem by replacing the derivatives, of which there are now 3, with finite difference approximations using neighboring nodes. This is the formula that we'll use in Jacobi iteration. Also note that if the annulus extends all the way to the origin, meaning it's a circular section, then we have many nodes in our discretized domain that correspond to the same point in space, the origin. To finish the video, let's summarize. We need to specify boundary conditions in order to have unique solutions to the Poisson equation. The finite difference method is a way to approximate solutions to problems like the Poisson equation. The first step is to discretize the domain. The second step is to discretize the problem. And the third step is to solve the discretized problem, obtaining a function defined on the discrete domain that we call our approximate solution to the problem. When we have Robin boundary conditions, we typically use fake nodes that are just outside the domain of the problem in order to solve for the values on the boundary. Finally, for increased accuracy, we use a finer discretization of our domain. That is, we decrease the distance between nodes.